All right, friends, welcome to today's lesson of 2.2 Inductive Deductive Reasoning. Two main types of reasoning, the way we think in the world of mathematics and in life, inductively and deductively. So we're going to talk about those today and some other vocabulary words. First one is what a conjecture is. A conjecture is an unproven statement based on observation. So you see something happening and you make a prediction of what you think is going to happen next, and that is called a conjecture. All right, so let's see what's happening with this exploration. Work with a partner. I want you to pause the video, answer these questions based on the Venn diagram that you see here. All right, welcome back. So hopefully you look a little something like this, friends. The first one, we've got a true situation. If an item is property B, then it has to be in property A. Yeah, everything in B is also in A. If an item is in A, then it's in B. No, not necessarily. You could be chilling down here somewhere. Part C is also false. If an item has property A, then it has to be property C. No, again, you could be over here. D, some items have property A, do not have property B. That's true. Could be there. E, if an item has property C, then it does not have property B. If an item has C, so C and B don't overlap at all. So there's a gap between them, so that's true. F, some items have both A and C, so they could be in that region, so that's true. Then G, some items have both properties B and C, and that is false. B all the way over here, C all the way over here with nothing touching. So more comment on that later. All right, so what we're learning today, inductive deductive reasoning. Here's our vocab. A conjecture is an unproven statement. We use inductive reasoning when we find a pattern in specific cases and then write a conjecture for the general case. So when you reason specifically to generally, then that is called inductive reasoning. You throw a ball up in the air and it comes back down. You throw a ball up in the air and it comes back down. So you make a prediction. Well, when I throw this ball up in the air, it's going to come back down. So you take a specific example to reason and say something in general, like every time a ball goes up, then it must come down. Whereas deductive reasoning is the reverse. It takes a general and says, I know there's a rule, there's a law of gravity that says if I throw this ball up, then it's going to come back down. And then you actually try it and it works. So deductive is when you go general to specific, and inductive is when you go specific to general. All right, so example 2, making and testing a conjecture. So let's see, numbers such as 3, 4, 5 are called consecutive integers. They're in a row. Make and test a conjecture about the sum of any 3 consecutive. So let's see here. So when we're doing this, we just want to pick some numbers. So 3, so we're talking about the sum. So 3 plus 4 plus 5 is 12. All right, let's do some other ones. 1 plus 2 plus 3 is 6. Let's just say 7 plus 8 plus 9 is 24. Do I need another one to see a pattern? Let's see. What about 6 plus 7 plus 8? That's 21. So now, do you see any patterns here? Do you see anything with this number as it relates to those 3? This number, or this number as it relates back? So let's make a conjecture. Let's see. Well, this one's kind of tough, but if I was thinking about this, 12 is just the middle number times 3. 6 is the middle number times 3. 24 is the middle number times 3. 21. Ooh, look at that. So all my examples keep giving me that same fact that whenever I'm adding consecutive integers, the sum is just the middle number times 3. So that would be my conjecture. So let's see. The sum equals the middle number times 3. So there's an example. All right, you made a conjecture based on the patterns that you observed, and that is inductive reasoning, based on patterns you observe, based on observations. All right, now a counterexample is a specific case when your conjecture is false. So if I were to find an example that would make this false back here, then that would be called a counterexample. To show that a conjecture is true, you got to show it's true for all cases. So you can show that a conjecture is false, however, by finding just one count. All it takes is one. One thing can throw the whole thing off. So let's look at example 3. A student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove the student's conjecture. And their conjecture is the sum of two numbers is always more than the greater number. So the sum of two numbers, I'm taking a number, adding it to another number. This person is saying that the sum, the answer, is always more than the greater number. So of these two. So they're saying, well, your answer is always bigger. How could we counter that? Well, you got to think in the world of negatives. To find a counterexample, you need to find a sum that is less than the greater number. And so if we talk about the world of negatives, so if we add -2 and -3, you get -5. And -5 is not greater than the larger number, which will be -2 in this case. So there's a counterexample, so therefore the conjecture is false. All right, now deductive reasoning, on the other hand, is not based on any patterns, but it uses facts, definitions, properties, laws to form a logical argument. This is very different than inductive reasoning, which uses examples and patterns. So in logic, deductive reasoning, we're going to say, well, I know this is true because, now here's a rule or a law because of it. And there's two types of laws of logic that we're going to be dealing with in this section. The law of detachment and the law of syllogism. So detachment says if the hypothesis of a true conditional statement is true, then the conclusion is also true. So if I have some conditional, P to Q, and I know that it's true, then I come back with the P part being true, then we're allowed to conclude that the Q part is true. And then for syllogism, it's kind of a silly word. If the hypothesis, then conclusion is true, and then the next hypothesis is just the conclusion of the first one to lead us to some new thing, R, then I can combine P with R in a new sentence. So now a lot of P's and Q's and R's, let's make it make sense. First one, law of detachment. So sometimes it's good to label these things. If two statements have the same length, there's your P. Then they are congruent. There's your Q. You know that BC equals XY. So that's them saying the P part is true. So remember what detachment said. Detachment said P to Q is true. And then if I know P is true, then I'm allowed to conclude that Q is true. So in this case, if two segments have the same length, they are congruent. And then we know that two segments have the same length, so we're allowed to conclude that BC is congruent to XY. So that's my conclusion. Now in example 5, here's an example of the law of syllogism. If possible, use the law of syllogism to write a statement that follows. So now check this one out. Here's your P to Q. If x is greater than 5, then x squared is greater than 25. Then they come back at you with that exact same thing in the next sentence. And then they introduce a new thing, which we call R. So if you have this link of the statements like this, then you're allowed to put together the original P and the ending R. So we'd be allowed to say that if x is greater than 5, then x squared is greater than 20. All right? So again, here's how it flows logically. If x is greater than 5, then x squared is greater than 25. If x squared is greater than 25, then x squared is greater than 20. So we took the first thing and put it with the last thing. So that is the law of syllogism. Now you have to be careful because sometimes it could look like this. All right? Now what they did here was they reversed the two sentences. So what you want to do is look. So like in this case, like I'm thinking PQ, but then this is something completely different, but then there's that P again. So if I just rearrange them, take this sentence up here and bring this sentence down here, if you can make it look like one of your thens is the same as one of your ifs, so one of your thens is the same as one of your ifs, then you can rearrange it to follow the law of syllogism. All right, now look at part B. Watch how this is different in part B. If a polygon is regular, then all angles in the interior are congruent. Now look at the second one. If a polygon is regular, there's your P again, then all sides are congruent. There's your R. But see how this doesn't flow logically? Like, because you'd think you want to say, oh, well, you can just put the first thing with the last thing, P with R, but it already is. That's what this sentence is saying here. So there's nothing else you can conclude to, you can't put the interior angles congruent with the sides congruent. That's not necessarily like if you can't say like if all angles in the interior are congruent, then all the sides are congruent. That's not the case. You could have a rectangle. All the angles of a rectangle are the same, but the sides aren't. So you have to be careful. It has to flow PQQR. This flows PQPR. So in this case, we would say no conclusion. So there's law of detachment, law of Sill. All right. Example 7, comparing them. Decide whether each inductive reasoning or deductive reasoning is used to reach the conclusion. So each time Monica kicks the ball up in the air, it returns to the ground. So the next time, it will return to the ground. So she's saying she's basing her conclusion on the patterns that she observed. So A would be inductive, based on patterns. And then B, all reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. So this is straight up deductive because you're using laws or rules or definitions. This one is based on your laws, all right, of detachment and syllogism. All right, pause the video here, try these, and see what you guys come up with. All right, welcome back. So here we go. Using the law of detachment, what statement can we make? So if 90 degrees is less than the measure of angle R, which is less than the measure of angle of 180, then angle R is obtuse. So P, Q, and then they tell us, look at this, the measure of R is 155. So now they're giving us a P value of being true. So I'm allowed to come at it and say that the Q is true. So the Q part is true. So in this case, that I could say that angle R is obtuse. So that'd be your answer. Law of Sill, write a conditional. If you get an A on a math test, there's a P, then you can go to the movies. There's a Q. If you go to the movies, oh, there's Q again. That's that same phrase. Then you can watch your favorite actor. So if this follows where the Q, the conclusion of the first one is the hypothesis of the second one, then we are allowed to match up the P with the R. So I can say that if you get an A on the math test, oh, this is a mess. It's so hard with this pen sometimes, party people. I'm just going to type it. Right? So my conclusion in this case would be if you get an A on your math test, then you can watch your favorite actor. So you see how we matched up the initial hypothesis with the final conclusion. And 11, decide whether inductive or deductive reasoning is used to reach a conclusion and explain why. So in this one, let's see, all multiples of 8 are divisible by 4. 64 is the multiple of 8, so 64 is divisible by 4. So here's P, here's Q, then they're telling you that the P is true, so we're allowed to say the Q is true. That is deductive reasoning, and your reasoning, that's the law of detachment in a nutshell, perfectly. All right, so that's 2-2, friends. Peace!